That was loud.
Great.
Well, then the stage is all yours.
Thank you so much, Ella, for your nice introduction and for the invitation. I'm really happy to be here to show you some of the research that we've done over the past few years. And so the title is Individual Preferred Rhythms in Brain Behavior, and it's quite a mix of different things I'm going to present to you today. So hopefully you will find some of it interesting. And so to start, I will basically talk about three different kinds, if you want, of rhythmic activity, rhythmic behavior rhythms today. The first one is brain rhythms, of course, so rhythmic neuroactivity at different timescales. I'm also going to talk about perceptual rhythms, and this is essentially just the perception of rhythmic stimuli like speech or music, or let's say quasi-rhythmic stimuli. And the third type of rhythm is motor rhythms, sometimes also called body rhythms, so the rhythmic activities that we do in our daily lives. And I will go into each of these in a bit more detail. And I would like to start with a deep dive into brain rhythms. And judging by the posters in the hallway, you all know what brain rhythms are. But just to bring everyone onto the same page, very, very quick, I'll just go through this very quickly to tell you what brain rhythms are. So these are rhythmic patterns of neuroactivity. And basically what happens is that populations of neurons like to fire at the same time at the same rate. And when this happens, we see this in the EEG, for example, as this up and down of the potential, and we can measure this in the EEG if. Okay, so working. Yeah, so it's continuing here, but not on there. Cool. Ah, yeah, okay, here we go. Cool. And we can measure this in the EEG or in the MEG if loads of neurons do the same thing at the same time. And brain rhythms are thought to be really, really important because they're thought to be responsible for the communication across brain regions and within brain regions and for information processing in the brain. And the last bit of information is that, of course, we have different time scales at which we can measure brain rhythms, from very, very slow activity, so once per second maybe, to really, really fast rhythmic activity and the gamma bands. Okay. And a few years ago now, we were interested in the prevalence of intrinsic brain rhythms. So where in the brain can we find what kind of rhythmic activity? And back then, so that was about 10 years ago, of course, we knew that alpha is really, really prominent. You can see alpha basically in the raw signal. And we also knew that the occipital, so posterior areas, really, really like the alpha rhythm. And then we could see delta sometimes, and theta and motor areas, but we really wanted to characterize the patterns of rhythmic activity across the whole brain. And what we did to do that is we used source localized MEG resting state data. So a data set where 22 participants just sat in the MEG for 7 minutes with their eyes open without doing any task. And in this resting state data set, we could then use different clustering methods, and I won't go into detail here, to figure out regional spectral fingerprints. And what this looked like is this. So I'll talk you through this figure. You see here the spectral fingerprints, that's how we called it, for the left and the right primary auditory cortex. So that's the Heschel gyrus. I show this one because this area is really, really important for my work, because I'm interested in auditory processing. So left and right auditory cortex are really, really important. And you see here the frequencies just from 1 to 30 hertz on the x-axis, and on the y-axis the normalized power. And whenever you see a little peak here, that means that this kind of rhythmic activity is very prominent in this area. So this, we can measure this in this specific area. And this is based on the majority of participants. So we only show those modes here, those peaks here, that the majority of participants have. So basically what this means is that all of us almost show this kind of activity in our left and right auditory cortices. Now what we see is that we have this delta peak, theta, alpha, and beta here. So these four rhythms are very prominent in the Heschel gyrus, in the left and the right Heschel gyrus. And I realized that I should have shown maybe one other area just for comparison, because yeah, this looks very similar, but we had other areas that look completely different. So some frontal areas, for example, only have a prominent delta rhythm, or we have some areas that only show gamma activity. I've cut the plot off here, so we tested this up until 120 hertz. Nothing much happens in our auditory cortex after 30 hertz, but there are other areas where we just have this really large broadband gamma mode that we find there. And if we look, for example, at the occipital cortex, we usually have two alpha rhythms there. So just two alpha peaks, and that's it. So you just have to take my word for it that other areas do look very different from this one. From this research, and it's not working again. From this research, we just continuing here. We could basically show that every brain area has a characteristic pattern of brain rhythms. We also replicated this in a different data set, in a data set that was recorded in Germany. And here are the two equivalent brain areas that I just showed you. And in this other data set, the spectral fingerprints look very similar. And if you want to try out to compute these spectral fingerprints yourself, there's a toolbox that came out recently. And basically all of these publications, this research showed that these brain rhythm patterns generalize across individuals. So all of us more or less have the same like principal brain rhythms in brain areas. But after that, I became more interested in differences across individuals. And I just want to show you that there are differences. So if we, and this is the same picture that you've seen before. So this is the left Heschel gyrus, or left primary auditory cortex. And I singled out the theta rhythm because that is, for speech comprehension, for example, is a really, really important rhythm. And what you see here are it's basically the average spectrum. So the cluster that almost all participants contribute to. But we can also trace this back to the individual spectra that the individuals contributed. And if I plot this, you see here all these, each gray line is basically a spectrum that's coming from an individual participant. And you see that there are differences. So there are differences in the individual peak frequency, and there are also differences in the individual peak amplitude. So from this, we can definitely say that individuals do vary in their peak frequency and in their amplitude of intrinsic rhythms, although most of us show like similar activity, but we still see differences. Now, these differences in intrinsic brain rhythms could be related to our perception and maybe our motor behavior. And indeed, there are some theories that assume this, or let's maybe call it account rather than theories. The first one is called the binary hierarchy brain-body oscillation theory by Wolfgang Klimesch, and I think the name didn't stick. I've never heard the name before, but that's what he called it. And it's from 2018. And among other things, so he talks about a lot of things in this theory, but he also mentions that our body parts have a preferred tendency to move. So he says that our like legs and arms, they all have an intrinsic frequency at which movement is, at which they would naturally move. And he also said that these body rhythms are coupled to brain rhythms. And importantly, he says that so there are phase-phase relationships and phase-amplitude relationships, and one frequency is always a multitude of another frequency. So let's say we have the alpha rhythm at 10 hertz in our brain. then our leg could move at 5 hertz, so half of the alpha rhythm. And yeah, he talks about a lot of things, but important for my kind of research is that he says our motor or body rhythms are related to our brain rhythms. And then there's another really important hypothesis by McAuley from 2006, and Paul Flass 40 years ago had similar ideas already, and that was called the preferred period hypothesis, where McAuley says that individuals have a preferred rate of event tracking. What that means is that we all, for example, walk at a different pace. Some of us like to walk slow, some of us like to walk fast. I walk very fast, for example, and so does my mother, and we often hear comments about that. And this kind of movement is thought to generalize to other actions as well. So I walk fast and I clap really fast and I like tap my finger fast. So all of my actions are pretty fast. But for others, all of this might be at a slower scale. And these motor behaviors are also thought to be related to preferred perceptual rhythms. And what McAuley did here was that he used participants' finger tapping as to measure the motor rate. So participants were asked to tap their finger at a pace that feels comfortable to them. And this is related to their general motor tempo. And they were also asked to say how much they liked series of beeps, and these were presented at different rates, so fast or slow, and the participants had to say which rate they prefer. And these two things were related. So participants who tap their finger fast also liked faster beeps. And these behavioral rhythms are thought to rely on intrinsic brain rhythms, so it all seems to be connected. At least that's the theory. And maybe here is a good moment to point out that this concept of perceptual preference can mean different things. So on the one hand, it can just mean what we like most. So participants are just asked, do you like this tempo? Do you like the other tempo? There are different paradigms by which this can be measured. But sometimes it also means the tempo that we perform best at. So what McAuley also did was they had participants synchronize with the rhythm they heard. And this synchronization was most accurate at their preferred rate. So this preference can mean the tempo at which you're good at or the tempo that we like most. And in theory, these two things should be the same. Okay, now I want to present some research that we did. And first I will talk about music. And there are not many studies that actually look at how our intrinsic brain rhythms could influence our perceptual rhythms or our preferred tempo in music. There is one study by Anna-Katharina Bauer that looked at the individual motor beta peak in participants, and they found that this predicts the preferred music tempo. So here you see the motor beta peak of participants, and here's the BPM of different music excerpts that they heard and which they rated. And you see there's a positive relationship. So those participants with the faster beta rates also preferred faster music, but of course with 11 participants, we would need to replicate that. So 11 participants, like anything can happen really. Yeah. Okay, whenever I use the pointer, it doesn't work anymore. So yeah, with 11 participants, yeah, not so sure. And from the same group comes another study where they found that the individual auditory gamma peak predicts the temporal resolution of auditory perception. So this is quite a broad finding, because at which rates we perceive our auditory worlds could potentially have influences on a lot of different things, like on our whole perception. So it's only loosely related to music perception, but it could potentially have consequences. So these two findings are basically the only ones so far, I think, that look into how intrinsic brain rhythms influence our auditory perception. And now I was most interested to find out whether individual brain rhythm peaks predict the music and rhythm tempo that we like to listen to. So similar to the above study here, but looking at basically all different frequency bands. So the first study I would like to show you, here we looked at the link between intrinsic brain rhythms and perceptual rhythms, in this case, our preferred music tempo. And this was led by back then undergraduate student Stratos Kokovinas, who's now a PhD student in Glasgow. And our perceptual preference task consisted of different drum grooves. So I wanted to keep it, or make it as similar to real music as possible, while at the same time it not being too influenced by different genres and different likings of participants. So we had 10 different drum grooves, and we presented them at different rates, and participants could choose the rate that they preferred, what they liked most. And that was between 70 and 170 BPM. I hope this works now. The first example is, I think, 110 BPM, so drum groove at a pace that most people quite like to listen to. Then the next one is very slow. That was a fast one. So we presented these different drum groups, and participants chose the tempo that they liked most. And that was our perceptual preference task. And for brain rhythms, we recorded resting state EEG. So this was just 5 minutes with their eyes open. And from those, we could compute our spectral fingerprints and then look at the differences for participants and the individual peaks here. So for Stratos' dissertation, we only did very rough analyses, so we didn't use any fancy statistics, and basically we just looked at EEG electrode positions and had an auditory ROI, so some central electrodes, and a motor ROI, which was slightly posterior, and said, okay, these electrodes, we know that they pick up activity from auditory and from motor areas, so that we're just going to look at these ROIs, and we just looked at theta and at beta. And I'm only showing you a preliminary analysis here of just 16 participants, because our undergraduate students only have a very, very, very short time frame to do a whole study. And if they do something big like an EEG study, it can become very challenging. So we basically just included those 16 participants in the dissertation, but then afterwards we continue testing, and now we have 32 participants, but I haven't analyzed those, so this is just a very preliminary analysis of those 60 participants. And what we found is that you see the tempo preferences of our 16 participants, and here you see the auditory theta peak, so just auditory electrodes, central electrodes. And there is kind of a small positive relationship, so the higher the auditory intrinsic theta frequency, the faster was also the tempo that participants picked or that they liked most. But with 16 participants, it's very shaky, so we definitely have to analyze the rest of the participants as well. For the beta peak, so what Bauer and colleagues found before, we didn't find any association between the beta peak and the tempo preferences of participants. But the beta peak was, so there were definitely methodological differences between the two studies. quite big differences, but also neither with 11 nor with 16, I would say. Both are really, really small sample sizes, and we definitely have to look at larger sample sizes. In the same study, we also had a motor rhythm task to get to analyze participants' preferred motor rhythm. So we're now looking at the behavioral relationship between motor rhythms and perceptual rhythms. So the perceptual preference task, you already know, so they had the groups and then they chose the tempo that they liked most. And the motor preference task was also a very, very classic task. It's often used where participants just tap their finger on the keyboard. And they were told to do this at a tempo that feels comfortable to them. And they did this for 20 seconds, 3 times. And in this analysis now, because the behavioral task could be easily analyzed, so this is now for all the 32 participants that we have. And you see here again the preferred tempo of our, in this case, 32 participants. And here is the ITI, so the inter-tap interval, so just the average time between taps. And when this number is really small, this means they tap really fast. The time between taps is really short. And when they tap really slow, like here, 1 second, this means the time between taps is quite long. And that's why this is a negative relationship. But basically what we see is that there's an association between the motor preference, so the finger tapping rate, and the perceptual preference. And those individuals who tap fast also prefer to listen to faster rhythms. But I'm very aware of this outlier here. So this is also something I need to look into. I think I've calculated this without this participant and it was still significant, but there's definitely some more cleaning to do to get rid of those outliers. So again, this is more preliminary. Okay, so to sum up the music part, if with more participants, we also find that the intrinsic auditory theta peak frequency influences the music tempo that we like, then one way this could be interpreted is that maybe if our intrinsic theta frequency matches what we hear more, this facilitates processing somehow, and that's why we like it more. But that would just be speculative at the moment. And then if after more cleaning, we find that the preferred behavioral motor rates and the preferred music rhythms are related, then this would be evidence for the preferred period hypothesis that my colleague proposed. But definitely we need larger samples to confirm this. Okay, and now I'm going to present 2 more little things about speech. So let's first look at, again, how maybe the brain and our individual brain rhythms could influence our perception. And there's one preliminary finding that I wanted to show you. So you already know this picture. So we've got our spectral fingerprints in the left hemisphere gyrus, and then we have these differences that contributes to the theta rhythm. And I had a data set in which I could basically roughly look at whether these individual differences in the theta rhythm contribute to our speech comprehension. So I had a data set where we had MEG resting state data. So I think that was again 7 minutes where participants didn't do anything. And from those, we got the individual theta rhythms. And in this case, I looked at the theta amplitude. And the same participants also did a speech comprehension task. And for the speech comprehension task, we had to find the individual signal to noise ratio. So there always was background noise when they listened to speech, and the background noise was adapted for each participant so that we had a performance of, I think, 75% where they could still understand the speech. And this was measured through an auditory staircase procedure. And this gave us the individual signal to noise ratio for each participant. So I'm showing you here, this is the individual theta amplitude that's coming from the resting state data. And here's the individual S and R for every participant. And if the number is like very, very negative, this means that these participants could deal with noise really well. So there could be a lot of noise and they could still understand the speech. And if the number is very small, this means they couldn't tolerate a lot of noise and they would just, comprehension would just break down. And you see that there's this negative relationship between the individual theta amplitude and the individual S and R, which basically tells us that the theta amplitude in heterogyrus during rest predicted speech comprehension and noise. So those participants with stronger intrinsic theta rhythm could comprehend speech and noise better, tolerate more noise. But this, so this data set wasn't meant to be analyzed in that way. So it's again, just very preliminary. But what we're doing now is that we look at these possible relationships in a much more systematic way. So we are currently doing a very, very big study, a population study, where we want to test 500 participants from the population. So from the population means we are really after all kinds of socioeconomic backgrounds and education backgrounds. So I wanted to get away from just always testing students. So we're trying to get a more diverse sample here. And this is funded by the Medical Research Council. And we just cracked the 100 participants. So we're getting there. So most of the legwork is done by postdoc Tanya Atanasova and research assistant Rosanna Timmerman. And what we do here is we again have our resting state measure, in this case 10 minutes. So we measure EEG while participants don't do anything for 10 minutes. And from this, we get the individual peak frequencies and the amplitudes in all frequency bands. And then we have different speech comprehension tasks in challenging listening situations where we try to, yeah, you could call it perceptual preferences. So where we try to find the, try to find out how good participants can do the tasks. And there's different situations that we have. We've got noisy speech, so similar to what I've just shown you. And we have different rates of background noise.
Has never done that before.
Okay,
Thank you.
so it's not working. So although we already have 100 participants, I didn't manage to analyze do any correlations between these two things, because we have the recordings of how participants respond to what they understand, but of course all of this has to be transcribed so that we can find out how much they actually understood, and this takes a long time, and we don't have a lot of these transcriptions yet. But something I could do relatively easily is analyze the spectral fingerprints of CZ, just because I wanted to show you something from this big study. So CZ is just the electrode that's at the top of the head, and we know that this picks up contributions from the auditory cortices. So both auditory cortices, both dipoles basically project to CZ. So this is a good test case to see what's happening in the auditory cortices. And here I just analyzed like the first 32 participants that were cleaned fairly well. So I'm not 100% happy with the pipeline yet, but just to show you something, I use these data. And these are again, the power here and the frequencies here. And you see that we have delta, theta, alpha, and beta rhythms or peaks here. And just to show you the comparison, this is the left primary auditory cortex. So this is source localized MEG data, and this is just CZ. And the rhythms seem to be like all there. Looks quite similar. So this gives us hope that we actually can do what we want to do, and that we can analyze spectral fingerprints in specific electrodes, and then hopefully source localize them as well at some point. But what we expect, our hypotheses were basically that there are some individual peak frequencies, for example, in maybe the theta rhythm, that predict the perception of fast speech. So people with a faster, let's say, theta rhythm and auditory cortex can perceive fast speech better. And that individual peak amplitudes hopefully maybe predict speech and noise comprehension. So similar to the preliminary analysis that I showed you before, we're hoping to find the same, of course, in our big data set with EEG data. Okay, and for speech, I've got another, yes, little study to show you where we looked at just behavioral tasks. And again, here at the relationship between motor rhythms and perceptual rhythms. So here we were, based on this idea that preferred motor and perceptual rhythms could be related, we wanted to see whether this is actually true for speech production and perception. So do those people who talk fast themselves speak fast? Do they also prefer fast speech, or can they understand fast speech better than people who talk slowly? And this was, yeah, this study is like a background story or an origin story, because I did this in, I think, 2019, just before COVID hit, with some students, and then the data set was just lying there. And a few years later, Christina Lubinos, who's a PhD student in Frankfurt, and Johanna Rimmler, we talked and we found out that we had done basically a very similar thing. So we had two data sets where we were interested in the same research question. So we decided to join forces and combine the two data sets, or report the two data sets in the same publication. So this means it's a dual lab study with one data set tested in Dundee, that was an in-person study, and the other data set was tested during COVID, so that was an online study that was done in Frankfurt. And both labs were or tested motor preference, so how fast people speak. And this was measured through the speech rate, and in the case of Dundee, we just had participants read out some text. It was the beginning of a story from a piece of paper, and we recorded them, and then analyzed the speech rate from the recording. And in Frankfurt, people spoke freely. So I think they had to talk about their favorite holiday or something, and people just talked freely, and this was recorded. And then again, we could analyze the speech rate. And for the perceptual preference, we both had speech comprehension tasks, but both very different again. So in Dundee, we had 7 different rates that covered speech that people could understand easily and repeat easily, to speech that was so fast that there was almost no comprehension. And again, people had to repeat what they heard, so it was quite a good measure that gave us like a lot of variance. And in Frankfurt, in the online study, people heard a sentence that could also be normal to quite fast. And afterwards, they saw 2 words that occurred in the sentence, and they had to say which one came first. So like an order judgment task. But although there were these big differences in the actual paradigms, we did find the same thing, which was nice. And what we found is that if you just look at the middle bit here, the preferred motor rate, so the speed at which people talked, predicted their speech comprehension performance. So people who talk fast also understand fast talking people better. And yeah, this was done with in these completely independently in 2 different labs with very different tasks, and we still found the same thing. We also recently replicated this, so this seems to be a relatively robust effect. Okay, to sum up the speech findings, so our intrinsic auditory theta peak amplitude could maybe influence our individual speech and noise comprehension, so that people with a stronger theta rhythm are better able to tolerate noise. And if we find this in the big study as well, then one interpretation could maybe be that with a stronger theta rhythm, we can maybe represent the actual signal, the speech, better. And this could lead to a better signal to noise ratio in the neural representation. That's just speculation. And when we look at rate effects, the preferred motor rate, our own speech rate, predicts our speech comprehension rate, and this is relatively robust finding. And to sum up everything, so we know that every brain area has a characteristic pattern of brain rhythms, and most of us show these same patterns, but we also see differences between people. So our individual peaks and amplitudes are all slightly different from each other. And this variance could influence our perceptual preferences and also our skills and our motor rhythms. And probably the most prominent theory that said this was the preferred period hypothesis. And I showed you some findings that seem to support these relationships, although now is maybe a good time to point out that it's quite tricky to measure participants' preferences, because you really rely on participants being compliant, so they actually have to really take some time to figure out what their preferred music or speech rate is, for example. And in online studies, for example, we don't really have compliant participants so much. So I've only shown you the in-person studies, but I've done a few online studies now where students get credits for taking part, and it seems to be quite tricky. So some of the studies, like the relationship is kind of always there, but whether it gets significant or not can change quite a bit. So yeah, I think these effects are quite difficult to measure. Time of day influences what we like, the tempo that we like to listen to quite a lot. Also mood, or like arousal or activity level, that really influences what we like to hear, and also our own motor rhythm, of course. So overall, I would say it's quite tricky to study. And from my experience, I would say that probably for every significant finding, like statistically significant finding that you can find in the literature, there's just the same number of studies that didn't find a significant effect. So I'm a bit wary here that there is a publication bias, and that we don't always find these relationships. And also the things that I've shown you were not super convincing. So I think there's definitely a publication bias at work here. But if we find maybe that after all, there is a robust relationship between brain rhythms and then motor rhythms and perceptual rhythms, then this could be a good point to maybe start improving intervention context. So I'm thinking, for example, about some Parkinson not treatment, but there are some studies that show that when Parkinson's patients move to music, then movements become like more fluent. And this kind of research could maybe suggest that if we use music that matches the participants' own motor rhythm really well, then maybe the improvements, temporary improvements, could become even bigger. So yeah, there's maybe some implications for intervention or for music therapy to use the tempo that matches the individual's own rhythms. And last, I just wanted to point out some initiative that we have that Laura also knows very well. So we founded this oscillations network. So it's called SCON because it's the Scottish Eucritical Oscillations Network. And because we're from Scotland, of course, we have to call it SCON. We had to make it work so that it could be called SCON, which you can check out here. And it's basically just a network of researchers who are interested in oscillations and who are critical. So at the moment we have I think more than 40 members from 10 different countries, but we're always happy to include other members as well. And just two of the things that we're currently doing. One is that we're working on a position paper. A position paper where we try to highlight all the open questions and problems that we currently have in oscillatory cognitive neuroscience. And that includes a lot of the questions about speech and music processing. And we also have an effect size project where we look into what kind of effect sizes we can actually expect from neuroscience research. And this is led by Laura, so she knows this very well. But there's lots of other things where you can get involved. Yes. So with this, I want to thank you for listening.